Okay. How's everyone today? What we're going to talk about today is covalent bonding, molecular structures. Now, you know what covalent bonding is, sharing electrons. You know what ionic bonding is, transferring electrons. What we're going to look at bonding that shares electrons. Understood? Now, this is going to be a pre-lab video on the construction of models following rules that are basic to molecular geometry. All of the rules, everything you need is on the drive, the Google Drive, in a folder labeled Gumdrop Lab. There's a PowerPoint presentation there. There's some reference material. Everything you need to perform the experiment, you have. Yes? I'm just going to give you some ideas on what it is that's going on relative to the lab. Correct? Easy?
Yes, sir.
Okay, so let's just look at a compound called hydrogen chloride. Okay, that's hydrogen chloride. Yes? Hydrogen is bound to chlorine. Correct? Hydrogen is covalently bound to chlorine. Easy?
Yes, sir.
Okay. There are There are 7 electrons around chlorine and 1 electron around hydrogen. Clear? Now this is the way atoms work. It's kind of like a land deal, you know? There are rules that govern, for instance, in the Old West. You had rules that govern shared government land relative to the grazing of cattle. You had certain rules relative to water use. You had certain rules relative to where on the range your cattle could go, etc. Clear?
Yeah.
You had to follow certain rules relative to branding, relative to identifying your cattle. Clear? Okay.
Yes.
So you had rules. Well, the same thing is true with covalent bonding. You have these kind of like land rules, you know. And what it is this. If hydrogen puts up an electron and chlorine puts up an electron, both the hydrogen and the chlorine can claim that electron that the other puts up as its own. So it forms a bond. So without getting too technical right away, we'll develop that as we go. These 2 electrons are shared by hydrogen and chlorine. So we know that in order for chlorine to be stable, according to the noble gas configuration of argon, let's write that down. So neon, and then 3s2, 3p5 plus 1, that will make neon, 3s2, 3p6, so it's gaining an electron, isn't it? Isn't it?
Yes.
This is chlorine. It's gaining an electron. So now it has 8, correct?
Yes, sir.
Yes. Hydrogen is 1s1. It'll go to 1s2, which is similar to helium, right? As opposed to the chlorine that is like argon. Correct? Are we all right with that?
Yes, sir.
All right, so you have the sharing of these electrons. Now, so far so good, yes or no?
Yes.
Okay. Now, if that's the case, then let me write that again. We have hydrogen and chlorine. Now, what is the electronegativity of chlorine? It's going to be 3.0, correct? Yeah. Now, you got to keep your electronegativity table out. You got to keep that somewhere safe. Hydrogen is 2.1. So what's going to have a greater pull on those two electrons? By the way, each dash represents a what? A bond, 2 electrons, correct? Yes. Okay. So, which one is going to have a greater pull on those electrons? Chlorine. The chlorine. And what happens is this, you get this shift. You get this shift of the cloud. This is like an electron cloud, correct? And you get this shift of this cloud. You get this shift. And if you put a line down the center, you see that there's a greater charge, a negative charge. It's not equal, is it? Over on the right side and less on the left side, correct?
Yes.
Now, does this make sense to you? Does this make sense to you? That this is Greek letter lowercase delta. You understand that? This is defined as partial. Okay? A very, very important Greek letter in bonding. It's partial. Are you with me? Lulua? Yeah? Everything's good? Okay. So, does this make sense? Tell me if it doesn't. Okay, Jan, are you with me?
Yes, sir.
Okay. That this side is a little negative, is a partial negative, and this side is a partial positive. Does that make sense?
No, sir.
It doesn't make sense?
It does.
It does make sense. Okay, good. So in other words, because you have this shift in charge, that side has a little bit more negative than this side. Well, if it's going to take negative, it's going to leave a little excess positive. Do you see that?
Yes,
okay,
sir.
good. Now, this is key. This shift in the bond charge. It's called, you put an arrow in the direction of the shift, and that's called a dipole moment. Yes?
What? Yes.
Dipole moment. Okay? You get it?
Yes.
Now, yes or no? We're there? So, when you have a dipole moment for a bond, you see there's only one bond there? Yes or no? Yeah. One bond, right? So, dipole moment, can we just say dipole? Is that okay?
Yes, sir.
We kind of like use a little slang. We just don't say dipole moment. You know, we just say dipole. That equals a dipole moment on a bond, right? Polar bond. So that bond is polar. You see that? It has a dipole. You see that? Yes or no? Now, let's do this. let's say I have let's say carbon dioxide, right? What's the electronegativity of oxygen? 3.5. 3.5. 3.5. 2.4 for carbon? Close enough? 2.5. 2.5. Okay, 2.5. Are we all right with that?
Yes.
All right, so what has a larger pull on the electrons?
Oxygen.
Okay, so this is 10, this is 1 is the difference, right? Here it's just 0.9. And that's a series dipole, by the way. Yes? That's a seriously polar molecule. It is. In terms of polarity, hydrogen chloride, very polar. Very polar. Not ionic. Not ionic. But
Polar covalent.
who said that? Professor Salmon, did you say that?
Yes.
Are you sure?
Yes.
You weren't fed that information by Jad?
I was fed that information by Mr. Nair last year.
Excellent. You remember. Very impressive. Very impressive. Polar covalent bond. So that's a series polar covalent bond. Look, the difference is only 0.9. Look at this. Look at this. It's 1. So wouldn't you say that this is very, very, very extremely polar? Yes? Yes or no? Right? So you have these gigantic dipoles. So let me ask you this. Are these two bonds polar? Are they polar?
Yes.
Okay. However, is the molecule polar? Oh, don't answer that. Do you think that this molecule is polar? First of all, there's only one bond. Do you think that molecule is polar? It is polar. It's a very, very polar molecule. Hydrogen chloride, very polar. Nah. Why is it polar? Well, I'm going to give you a hint. Intuitively, would you say that that is a polar molecule or a non-polar molecule?
Polar.
All right. These are drawn like, almost like vectors, aren't they?
Yeah.
Yeah. Okay.
Polar means they're sharing equally, right?
All right. Let's say I have two vectors. This vector is pulling that way. Okay. Yes. This vector is pulling that way. So they're equal. Are you going to get any movement? No. Right? Right? They're going to cancel, aren't they?
Yes, sir.
Excuse me?
It's one product, so it's like this one product.
The accent is, I think you're a wonderful person, and my ears, what does it say?
So it becomes non-polar because
It becomes non-polar.
the charge equal out in opposite direction.
Yeah, they literally cancel. It's literally like vectors. It's literally like a tug of war. You could certainly think of it that way. That is not a problem. You see how these cancel? They cancel. They literally cancel. Are they the same size?
Yes.
They're going to cancel. Is there anything here to cancel this?
No.
No, there's not. Polar, non-polar. What about the bonds? Polar bond, yes or no?
Yes.
Polar bond, yes or no? Absolutely. Polar bond, yes or no? Absolutely. So now, do you see that there is possibly a structure to a molecule that will give way to polarity of that molecule? Let's look at another example. One that's a little bit more complex, okay? All right?
Sir,
Yes?
what is this video going to be called?
I don't know yet. I'll make it very, I don't know. I'll make it very obvious, okay? Let's take one I made the mistake on. What was that? Methane? Yes, it was methane, right? So, now Now, it's hard to draw a methane molecule on a board because it's two-dimensional, and methane doesn't look like that, but it's close enough. Okay. What is the electronegativity of hydrogen is 2.1, and carbon is 2.5. Not much of a shift, right? More or less, right? A little bit shift, yeah. Okay, so this will look like this, right? Okay, fair enough?
Yes, sir.
Okay, cool.
Isn't that triangles mean forward?
The triangles is just my poor representation of a cloud that shifted towards the carbon.
So I'm going forward or backwards or sideways?
The place where there is the most is the one that is more electro.
Yeah, the cloud shifts towards the more electronegative, right? Remember that? Are you with me?
Yeah.
You sure?
No, I was
Yeah.
just asking. I thought you didn't. I thought you were saying because you know the shape sometimes refer to a position.
The base is negative. Just
Yeah, see?
The base of the triangle is more negative.
Yeah, in other words, this is a cloud. This is a cloud. That's simply, there's a cloud. This really looked like this, but it shifted this way, so it looks like this. Just shifting, that's all. In other words, I'm shifting the electrons this way, so it's going to look like a cloud. It's a little bit too perfect of a drawing, but I just tried to make it simple.
I thought you were doing Vesper.
You thought yeah, we are. We are doing Vesper. What? You're confused. Let's.
Because you know Vesper is like a thing triangles backwards and dotted triangle something is.
No. I'm not. No. I'm not doing. No, that's just to show the three-dimensional. They put in like little slivers of. But that's not what we're doing. No. That's not what we're doing. That's just showing. No, those triangles in molecular presentation are simply to show a three-dimensional structure. That's all that is. That has nothing to do with Vesper or anything else. That's just a way of drawing a molecule.
Well, we took it last, that's why.
Excuse me?
Because you said no, you can't draw on a two-dimensional board, so I just thought you were doing.
Oh, no. This is not one of those triangles that I'm using to represent a three-dimensional molecule. This is simply, the red is simply, solely and only, the cloud that's shifting towards the more electronegative element. So more of the cloud is by carbon, less of the cloud is by hydrogen. You have 2.5 is stronger than 2.1, that's all it is. Yes?
Isn't methane a drug?
No. Methane is not a drug. Methane is a gas. It's a single carbon, 4 hydrogen, hydrocarbon gas, methane. I'm not sure.
He thinks it's a methamphetamine.
Oh, methamphetamine. No, this is not a methamphetamine. No, that's very different. No. Okay, you get it?
Yes, sir.
Do you understand? Okay, now. Do these dipoles cancel? Do these dipoles cancel?
Yeah.
Yes or no?
Yes.
They absolutely do. Would this molecule, methane, be polar or non-polar? They'd be non-polar. So methane is non-polar. Clear? Okay. So you understand the whole concept of the electron cloud shift. You with me?
Yes.
Okay. So let's do this. Let's speed this up a little bit, and we know that we have shifts, etc. Okay. Okay, so where are my dipoles here? I know I have shifts, so let's draw the dipoles. 2.5, 3.5, 2.2, or 2.1, 2.1. So this is going to be this way. This is going to be this way. this is going to be this way, and this is going to be this way. Correct? These two cancel, do they not?
Yes.
They're equal and opposite. Do these two cancel?
No.
Absolutely not. So what would you say about these two? These create a polar molecule. Yes? Yes or no?
Yes, sir.
Okay. So this is where we're coming to right now. We're almost finished. Okay? Professor,
Yeah,
you're paying attention with.
yeah, I just found this note card that teaches you about IV symbols.
I think that's a wonderful distraction, but let's try to maintain focus. Okay. Excellent. All right, now, so let me do this. Let's say I have water. So, this is where we're going, okay? On my next video that I'll make with tomorrow's class, I'll be a little bit more organized. I'm just trying to do a quick intro, okay? Yes. Jan, you with me?
Yes, sir.
Doesn't seem that way.
I'm just.
Okay, let's focus up here. Okay, good. So, what you do is this. You have the formula. Now you have to think. What goes with which? Okay? Do hydrogen bond together and then a hydrogen, in other words, do I say H, H, O? Is that how it goes?
No.
No. That wouldn't work, right? Because hydrogen can only have one bond, right?
Yes.
This gives hydrogen 4 electrons. How many electrons must nitrogen have? Like helium, which has 2, right? So that would be wrong, correct? Okay.
Oxygen is in the middle.
Oxygen's in the center. Okay, good. So that's what happens. Oxygen's in the center. Do you have your gumdrop lab out?
Yes.
You have it on your computer?
Yes.
Okay. So you want to look at that. You want to open up the PowerPoint.
Your turn isn't working.
Okay? Internet's not working? Okay.
Come on. Let's just read.
Okay, now that's number one. So number one, step one, you draw the model, the basic skeleton model. Clear? HOH. First step, correct? You put a single bond in. Clear?
Correct.
You draw a single bond. That's all you do. You ready? Okay? Next thing you do is, it's an accounting procedure. You put in the valence electrons. How many total valence electrons are there? Okay. What column does hydrogen come from? First. How many valence electrons does it have? 1. So 1 each. So you say 1 and 1, okay? What column does oxygen come from, and how many valence electrons does it have? 6. Okay? So 8 electrons. Make an 8. Yes? Now, the idea is you have to get down to 0. You have to get rid of all the electrons, you have to distribute them and get them all done. Clear? Okay. So you want to subtract off from 8 2 electrons per bond that you have. How many electrons do we have in the bonds? How many? Okay. There's 2 here and 2 here. Where do you get 8 from?
I'm sorry, for oxygen, there's.
Yeah, but that's not what I said. I said, here are the total number of electrons. Valence, valence, valence. That's the total, correct? Then I said, this is all I said, you want to subtract off from the 8, 2 electrons per bond. So how many bonds are there? 2 bonds. So how many electrons does that represent? 4. So you subtract off of 4, you're left with 4, correct? Now, this is key. Listen carefully. This is very important. Okay. How many electrons does a central atom have to have if it's a non-metal?
Can you repeat the question?
Okay. If the central atom is a non-metal, how many electrons, could you excuse me for a second, everyone back home? I just got to do something really quickly. Not really.
What?
Or you can be speaking after class. Stop going around.
I was gonna-
Excuse me, it doesn't matter. You've been annoying me for the last 2 minutes.
All right.
Is that clear?
Yes.
Is that good?
Yes.
Excellent. Okay. So, if the central atom is an oxygen or a nonmetal, how many electrons, what's the minimum number of electrons must it have? It's got to be like what? Look at the periodic table. Look where oxygen is. What does it react to be like? It reacts to be like what?
Neon.
Neon. Right? Okay. So how many electrons does it need? No. How many total electrons must oxygen have in order to be like neon? You guys, I know this is the end of the day and you feel like you just went through the rinse cycle, but can we do this like I've actually taught something over the last 8 days? Yes?
8 electrons.
8 electrons. Very good. So what you did was you thought I would suffer up here, withhold the answer to see whether or not I had a meltdown. Is that correct?
Exactly.
Excellent. Okay. So it has 4. How many more does it need?
4.
So I have 4 right here. So I put in
Lewis.
2 pairs, right? Do they have to bond with anything or they can just sit there?
They can just sit there.
Yeah, because hydrogen doesn't need any more bonds. So I have 2, 4, 6, 8. It's done. Correct? Now, then what you do is, then you're going to say, right, this
Wait,
is,
Can you repeat that?
okay.
The one about it already has 4.
It has 4,
Yeah.
2 and 2. This is oxygen, right? It has 2 and 2, that's 4.
Yeah.
It needs 4 more.
Yeah.
Okay? Okay, now. Here is oxygen, right? This is oxygen. Here is hydrogen. Okay? Here's hydrogen. Okay? This is what you guys are going to do. Okay? Here's hydrogen. Now. So you make a little ball of clay, right? Now, what kind of geometry is going to have 2 bonded pairs and 2 non-bonded pairs? Look through the handout.
Bent.
Look through the handout.
You're right on
I'm
time.
filming, so let's try to keep quiet. Thank you very much.
It's bent.
Okay? Excuse me?
Bent.
What, how did you find out that? You just look up the worksheet, right?
Yeah.
Okay? Guys who just came in, you have about 6 minutes and you guys can be right on target. If you get out, go with somebody and look on, and they're on the Google Drive and we're doing the Gumdrop Lab pre-lab. Okay? So it's got to be bent, right?
Yeah.
Okay, good. So this is what it looks like. Okay? This is what it looks like. You ready? You ready?
What was bent 2?
If you have 3 electrons, okay? I'm sorry, 3 atoms, and you have 2 bonded pairs of electrons and 2 unbonded pairs of electrons, it's going to look like this. See that? You see that?
Yes.
Okay. Now, understand this, that they have to be opposite from one another. You see that? That's bent. That's called a bent geometry. Clear? You see that? It's called a bent geometry. What's bending them out? What does VESPR stand for?
Valence shell electron pair repulsion.
Valence shell electron pair repulsion. So, if I didn't have these here, wouldn't it look like this? It would look like that, right? You see that? But because I have these these here, these are pushing the bonds, the pipe cleaner pieces are the, see that? See how that is? You see that? Cool or what? This is what you're going to have to do on Wednesday. Okay, now, so let's do one more and then quit, okay? Because I'm going to make several videos tomorrow. So we'll do one more and then quit, okay? And I'm going to make one. Now, let me ask you this. Just thinking about it, would you say that that's polar or non-polar?
Polar.
It's polar because it looks like this. Because if I have hydrogen, these dipoles are going like this, aren't they? They're going like this, aren't they? Right?
Sure.
So I'm going to push my forearm, I'm going to go this way. This forearm, I'm going to go this way. It's going to go straight, right? It's going to go up, right? You get it? Okay. Let's do one more and then we'll quit. Okay. Guys, thank you very much for coming. I know that you had a very busy day and it was very intellectual, etc. We don't even want to go in there, into there, but that's okay. I'm flexible. Okay. All right, so let's do this one. NH3. Right? Ammonia, NH3. Okay? And then we'll quit. Yes?
Yes.
So obviously it's going to be N like this, right? Right?
Yes.
So you take down your valence. 8, correct? 5, 1, 1, 1, correct?
Yes.
Subtract off 6 because I have 2, 4, 6. I'm left with 2. Remember, a non-metal that's central has to have at least 8 electrons. Yes? It can't have less than 8. That's a rule. It's right in your packet. Okay. So I've got to put these two here. All right, now let's make the model and then we're going to quit. So we're using nitrogen. We're going to say nitrogen is blue. I like blue for nitrogen. When I think of nitrogen, I think of blue. I have no idea why. Okay. I went to the new mall on Friday.
Yeah, small.
Yuck. Awful.
What's wrong with it?
Big, expensive. They didn't have any food. They didn't have anywhere nearly enough places open for food for people who were hungry.
Burger King.
Yeah, like I was starving and it was like the lines were like a mile long. But I will recommend this. Go Friday morning. There's nobody there. There's nobody there. Because I went Friday late morning, early afternoon, and it was, when I first got there it was fine, but then it got a little crazy. Okay?
Because Rita Ora came.
What is it?
Because a celebrity came.
What celebrity? What are you talking about?
Rita Ora,
Who's Rita Ora?
some singer.
She's an artist.
She's an artist. All right, let me get some. All right, I'm almost done. Hang in there, bear with me. Okay, I'll use the big guy. I'll use big guy. So it goes like this. You look at your chart, you say, when I have 3 bonded pairs and 1 unbonded pair, what kind of geometry is that?
Organal plan.
No, look at your chart.
Trigonal pyramidal.
Trigonal,
Pyramid.
trigonal, trigonal, pyramidal. Okay, ammonia, right? So this is what it looks like. It's not terribly out of the, it's not like way down. It's just slightly out of the plane, right? Yes? See that? That's trigonal pyramidal or trigonal.
Trigonal planar.
What did I say? No, it's trigonal pyramidal.
What's planar then?
Well, I really don't want to, I'll surprise you. Because everybody's kind of itchy. Okay? And I don't blame them. Okay? Where's everybody else? They just,
The lady on the bus from this part 2 or something said that since we have 15 minutes left, she excused everyone for the day. But we can't, 'cause we wouldn't sit.
you guys are so wonderful. Wonderful. I'm very impressed. All right? We're done.
That's the